Alright, let's continue working through these example problems, and going on to NH3, we'll come across some of these that there are some exceptions and some strange things that we have to consider. Let's start with NH3. N is in group 15, so that means it's got 5 valence electrons. Hydrogen is in group 1, so it's got 1 valence electron, but we're multiplying by 3 because we have 3 of them. So this is 8. Okay, 8 valence electrons. Connect each of these with 1 bond. It's important to remember that hydrogen is one of those exceptions. Hydrogen does not want 8 valence electrons. It's the most important exception. I would say hydrogen, because it comes up a lot, is more important to remember than boron or beryllium. Hydrogen only wants 2 valence electrons. And if you look at this, each hydrogen has 2. Right? Each hydrogen has 2 valence electrons. So if we're doing that outsider step, we've already got it. The outsiders are happy. If we have any leftovers, where do they go? Leftovers go on the central atom, which works out well because nitrogen actually wants 8. I've got 2, 4, 6, 7, 8. Okay. We did our leftover step. Now we just check if everyone is happy, and if they are, then we're done. So hydrogen has 2, which is what it wants, and then nitrogen has 8, which is what it wants. We're done. Okay, let's look at H2O, or water. 1 times 2 plus 6, and don't forget to do your count, even if you think you know what the structure looks like. Okay. 2 plus 6 gives you 8. So we have a single bond connecting them. We've got 2, 4. Hydrogen only wants 2 electrons. So our outer atoms are happy. Next thing we do after the outsiders is look at our leftovers. I have 2, 4. I have 4 more electrons left. Okay. So 2, 4, 6, 8. The leftovers go on the central atom. And if we check to see if everyone's happy, hydrogen's happy, and oxygen has 2, 4, 6, 8 now. We're done. Now let's look at H3O+. Remember, with ions, you have to consider the charge. So when we do our math, we're going to have to consider the charge here. Hydrogen has 1 valence electron multiplied by 3. And then we've got oxygen with 6 valence electrons. If we have a positive charge, that means we're going to have fewer electrons by whatever the charge is. This is a positive 1 charge, so that means I'm going to have 1 fewer electron. That means I need to subtract 1. So I have 6 plus 3 minus 1. 6 plus 3 minus 1, which is 6 plus 2, which is 8. Okay. Don't forget to put a positive charge outside of the brackets. We're going to connect each of these with a single bond. Hydrogen only wants 2, so we check our outsiders. Hydrogen is happy, 2, 2, and 2. Okay. And then what would we do with our leftovers? So I've used 6, that leaves 2 left over, and the leftovers always go on the central atom. So now we just check to see if everyone's happy. We already decided the outsiders, hydrogen is happy. So let's look at oxygen. I have 1, 2, 3, 4, 5, 6, 7, 8. It's happy, and we've used all of our electrons, so we're done. SO2 or SO3 with a -2 charge. Let's look at this one. Sulfur is in group 16, and so is oxygen. So we have 6 plus 6 times 3. And then this -2 charge means I'm going to have extra electrons. To be exact, because it's a -2 charge, I'm going to have 2 extra electrons. So we're going to add 2 electrons. Okay, so I have 24, 25, 26. I have 26 valence electrons to work with. We start with single bonds. 1, 2, 3. Okay. Then we make our outsiders happy. So I have 2, 4, 6, and we cannot exceed 26. Remember that we can't have more than 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and then 26. The last pair goes on the central atom. After we've made all of the outsiders happy, if we have extras, they go on the central atom. Now let's count to see if everybody's happy. We already checked all the outside atoms, 2, 4, 6, 8. They all look the same, so oxygen's happy. Look at sulfur, 1, 2, 3, 4, 5, 6, 7, 8. Sulfur is also happy. So we're done. We just need to make sure that we write 2- on the outside of the brackets. All right, and then SO3, this is different. It looks the same, but it's different because SO3 and SO3 2- are not the same thing. The one on the left is sulfite. The one on the right is sulfur trioxide. It's a covalent compound with no charge. Okay, so I've got 6 plus 6 times 3, but I don't add the extra 2 electrons. So instead of 26, I've got 24 electrons. Start with your single bonds. All right. Now we're going to keep going on the outside. Remember, we cannot have more than 24 electrons. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, we made the outsiders happy. Do we have any extra? Do we have any leftovers? No, we used all of them. Okay, so if we remember our steps, after leftovers we check, are they happy? Okay, if there are not enough electron pairs to give the central atom an octet, we're going to make multiple bonds, double or triple bonds, and then we just double check to make sure that they have at least enough electrons. So as we look at this, sulfur is not happy. Okay, oxygen is, but sulfur only has 6. So what we need to do is take one of the electron pairs from oxygen, and it can be any of these. We could take it from here, or here, or here. It really doesn't matter. And make a double bond. Okay. By the way, because I don't have a lot of room to write on here, instead of making that double bond, I'm going to, or instead of redrawing the whole structure, I'm going to just erase that electron pair and draw a double bond right here. And then you can do your final count, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everybody is happy, and we have the right number of electrons. We have a total of 24 electrons. All right, let's do CO2. Carbon has 4. Oxygen has 6 times 2. So we have, oh, and one thing I want to mention, oxygen has an atomic number of 8. but it's in group 16. A lot of students, that's the one that gets messed up the most often, is oxygen and carbon. A lot of students will just look at the atomic number and they'll make a huge mistake here. Always look at the group number, not the atomic number. So 4 plus 12 is 16. Start with single bonds. Then we want to check if we can make the outer atoms happy. So 2, 4, 6, 8, 10, 12, 14, 16. So 2, 4, 6, 8, 10, 12, 14, 16. Is everyone happy? The outsiders are happy, which is what our first goal is. Do we have any leftovers? No, we don't have any leftovers. So that step can be skipped. Then we need to look at whether they're happy. So we're going to check if we need to make some double or triple bonds. With CO2, carbon is the one that is not yet happy. So we can take a couple electrons from oxygen and move it down here. That would give carbon 2, 4, 6 electrons, which is still not enough. So we've got to go over to the other side and grab 2 electrons and move them down so that we could share those. We would have 2, 4, 6, 8, which is exactly what we need. And if you check it and count those, you would find that carbon and oxygen, both of the oxygens and the carbon in the middle, they're all satisfied. They all have 8 valence electrons surrounding them. Let's look at C2H6. This one looks really weird because we have 2 central atoms. Okay, let's start by connecting each atom to an outer atom. Okay, so I'm going to start with that, and then we've got to connect it all together somehow. So we're going to draw a single bond here as well. Okay, I should have done my math first. Let's do that now. 4 times 2 gives us 8, plus 1 times 6. So we have 6 plus 8 gives us 14. Let's count those. 2, 4, 6, 8, 10, 12, 14. We've used them all up. There's no extras, so we don't have to do the leftover step. Hydrogen only wants 2, so that means our outer atoms are satisfied. Now let's check if the central atoms are satisfied as well. Carbon has 2, 4, 6, 8 around it. The other carbon has 2, 4, 6, 8 around it. Everyone's happy, and that's all that we have to do with this one. All right. The next one's a little bit more involved. N2O4, nitrogen has 5 valence electrons. Let's multiply by 2. Plus oxygen has 6, multiply by 4. So that's going to be 10 plus 24. Gives us 34 electrons. Okay, 2, 4, 6, 8, 10. Okay, we've got 24 electrons left to work with. Start with the outer atoms. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, and then 34. Outsiders are happy. I don't have leftovers, so I skipped the leftover step. Then we ask if everyone's happy. all of the oxygens are happy. They each have 8 around them, but nitrogen has only 6 around it. So what can I do to fix that? Well, I can take 2 valence electrons and share them, and that would make this nitrogen atom happy. It would make this one happy. The other one would still be unhappy, so I could take 2 electrons from one of the others and share it there, and that would make this nitrogen happy. So to do that in a little more clean way, let's erase 2 electrons, draw a double bond, erase 2 electrons here, draw a double bond, and now both nitrogens are happy and the oxygens are still happy. 2, 4, 6, 8, 2, 4, 6, 8, and the other 2 oxygens we did not touch. So we're done. All right, XEF2 is the last one I want to do before breaking for another example problem video. XEF2XE is one of those noble gases. It has 8 valence electrons, so we have 8 plus, and then fluorine has 7 times 2. Okay, so we have 14 plus 8, that's 22. Okay, single bonds first, that's 2, 4, 6, 8, 10, 12, 14, 16. Okay, I've used 16 and fluorine's happy. So outsiders are happy. Let's keep track of this one because it's a little bit more. Okay, so I've taken away 16. Now let's look at xenon, the central atom. It's got 2, 4. I could use a couple of those. 6, 8. Okay, so I used 4. Okay, so that means I've actually subtracted 20 total, right? I've used 20. That leaves me 2 more electrons to use. Now, you may say, well, what can I do with that? I mean, they're all happy. They all have 8 valence electrons. Well, remember, you can have more than 8 valence electrons on the central atom. So what we're going to do is put those leftovers on xenon. The outsiders always need to be happy. In some cases, you're going to have more electrons on the central atom than it actually wants, as it is in this case. So fluorine has 8 around it. Xenon has 10 around it. 2, 4, 6, 8, 10. But that's just the way it is because we have to use all of our electrons. This is an expanded octet problem. So we're done with number 12.